Okay, in this video, I'm going to talk about how to calculate Kb for a weak base. It looks kind of similar of that of the Ka, except you have to remember that we're dissolving these weak bases in water, and that's how we're making that OH. And then I'm going to talk about the relationship between Ka and Kb because they're kind of interconnected. Okay, so let's look at an example here. So it says calculate the pH for a 15 molar solution of ammonia if it has a Kb of 1.8 times 10 to the negative fifth. So like always, we're going to write our chemical reaction, okay? And so like I said, we have to add water as one of our reactants because we need something for that NH3 to give up to accept a proton from. So it's going to accept a proton from water, okay? So with that being said, since bases accept protons, one of my products will be NH4 plus, and the other one will be OH minus, okay? And this is why it makes the solution basic, is because it makes OH, okay? It has nothing to do with NH3. Well, I mean it does, but technically speaking, the OH is what makes NH3 basic because it accepts a proton to make that OH, okay? So then if you set up a Kb expression for this, you have to remember liquids and solids aren't included in equilibrium expressions, so we'll omit water, and then we'll have NH4 plus times the OH concentration divided by the starting concentration of NH3. And then these problems look exactly the same. You can do a Rice table if you want to. So I have my equation, so I'm just going to do ICE. Okay, so initially it tells me that I have 15 molar of NH3. Water is not involved, and then I have 0 of both of the products. So then the change in is going to be just like acids, minus X plus X plus X. So then it's going to be 15.0 minus X, X, X. And then just like before, we can omit the minus X because it's very small and tangent to the 15 molar that we have. And then you can just plug it into your equation. So the Kb is 1.8 times 10 to the negative fifth. These are both X, so it's going to be X squared divided by the starting molarity, which is 15 molar. And then you do X squared is equal to this times this, times 15. I get X squared is equal to 2.7 times 10 to the negative fourth. And then I take the square root of both. So X is equal to 0.0164. And we have to remember that this is the concentration of OH, okay? Now, we can solve for the POH, but we have to remember that we have to go one step further because our scale is based off of pH, okay? So POH is equal to the negative log of OH, which is equal to the negative log of that 0.0164. So the POH is equal to, calculate that, 1.79, but I want pH, so I'm going to have to do 14 minus the POH and see what I get. So I get 14 minus 1.79, so I get a pH that's equal to 12.21, and that makes sense because it's a base, right? So we would expect our number to be greater than 7, and it is. Okay, so that's how you calculate KVs for weak bases. Now I want to talk about the relationship between Ka and Kb. Okay, so let's kind of get a definition down here. Okay, so this is section 16.8, sorry, the relationship between Ka and Kb. Okay, so let's sort of get a definition here. The product of the acid dissociation constant for an acid, okay, so that would be Ka, okay, and the base dissociation constant for its conjugate base, which will be the Kb, okay. So when I say this, I'm saying Ka. When I'm saying this, I'm saying Kb, which means you have an equilibrium constant. Okay, so it means you have an acid dissociation moving forward, and you have a base dissociation moving backwards in the reversible reaction. So mathematically, what does that look like? Well, that looks like this. That just means that we're saying if you have an equilibrium between a weak acid and a weak base, the Ka times the Kb should be equal to that Kw, and if you remember what Kw is, it's 1 times 10 to the negative 14. Okay? So with that being said, if you're given a Ka of a weak acid, you can find the Kb of its conjugate base by using the 1 times 10 to the negative 14. And again, this only applies to the conjugate acid-base pair. So this has to be a single acid-base equilibrium expression. Okay? And then there's two other things that we need to talk about, and that's the pKa and the pKb. So you guys did a problem where we just assumed that pKa was Ka, but that's not actually true. Okay? So the pKa is actually going to be equal to the negative log of Ka. Okay? Which then means to find the Ka, then you would do 10 to the negative pKa, or to find Kb, you would do 10 to the negative pKb. Okay? And just keep that in mind because we'll come back to this when we go more into weak acid-base titrations. Okay? All right, so that's pretty much it for this section. Problems like this look like I just said, you're given Ka, solve for Kb, and you just plug it into this equation and solve. So that's it for Kb, Ka, Ka, Kb relationship.